Golly, technical difficulties. Anyways, as I was saying, an asymptote, it's a line that your values approach. They get really, really crazy close to, but they don't actually ever get to touch it. And so they might hop over it, like they suddenly just jump over that value. But usually the ones that we come across, they just get closer and closer to, but they can't cross over. Okay. So now let's go look at these examples. You will definitely need your graphing calculator for all of this lesson today. So let's go to a new document. Definitely not saving. And we're definitely using a graph. So we're going to type in this tiny little equation of 2 to the x power. So to do that, you're going to type 2 caret x. That's what you're going to type. And it's so little, it's just hard to see. So 2 caret x. Push enter. Isn't that a different looking graph? So here we see that this curve gets crazy close to the x-axis, but it does not appear to cross over that x-axis or go below the x-axis. It definitely does not drop down here, like below down there somewhere. Nope, not at all. So let's go run the numbers and see what they look like. And yeah, this graph goes -10 over to like 3. So let's make a t-table for that. X and Y. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That should be enough. Let's start with 3, 2, 1, 0, -1, -2, -3, -4, -5, -6. That should work. Okay, time to get out your calculator. So, Control T. Oops, there we are. So x equals 3, and I have a height of 8. All right. X is 2. I have a height of 4. Where x is 1, I have a height of 2. At 0, I have a height of 1. Now watch this. It gets so little, but it doesn't cross over to oblivion. Let's find out what that means. So I have 0.5, 0.25, 0.125, 0.0625, 0.03125, 0.015625. Look how tiny those numbers are. But you know, we could keep scrolling here to negative land. And this is just going to get smaller and smaller, but it will never go below the x-axis. It's just not. That's crazy. So let's go graph it. So I start off with the point 3, 8. Right 3, 1, 2, 3, up 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 4. Can those fit? Yeah. 2, 1, 2, 3, 4. 1, 2, 0, 1. So you see how this is not a straight line at all. It curves. Let's check this. Left 1 up a half. Left 2 up a quarter. Left 3 up 12 cents. Left 4 up 6 cents. 5, 3 cents. 6, 1.5 cents. I mean, oh my gosh, that's so tiny. But it does not cross over. Do you see that? Cool. So this is y equals 2 to the x power. And our asymptote so the line that we got closer and closer to reaching is y equals 0. It has a height of 0. The x-axis, you could write it both ways. The x-axis, which is also y equals 0. There you go. Kind of cool. All right, let's go try another one just to see how this is similar, but yet still kind of different at the same time. So again, I'm going to make a t-table, and I'll make it x and y with 10 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only because I know what's coming, let's start at -3. -2, -1, 0, 1, 2, 3, 4, 5, 6. So, Control Doc. Let's go get a new graph. And for this one, to type it in, I'm going to use parentheses, 1/2, and then a caret mix. So that's what I'm typing in. Parentheses, 1/2. So you could either use Control Divide to get that 1/2, or you can just say 1 divided by 2. That slash is a divide. Caret x. Check that out. It's going the other direction. That's kind of crazy. So let's go look at its table. Control T. And hello. And let's see, we started at -3. My lighting is just weird all of a sudden. I don't know what the issue is. Sorry, folks. -3 has a height of 8, and then 4, and 2, and 1. Are these numbers looking familiar? And 0.5. And then 0.25, 0.125, 0.0625, 0.03125, 0.015625. Yeah, those numbers look very familiar, but they're located someplace different. So let's go see where they're located. So this is -3, 8. So if I go to the left, 1, 2, 3 units, up 8. There it is. And then to the left, 2, up 4. Left 1, up 2. Over nothing, up 1. And then 50 cents, 25 cents, 12 cents, 6 cents, 3 cents, 1.5 cents. Totally cool. So what did we see in our pattern of behavior for our graphs? Well, my two equations are very related. This 1/2 and this 2, they're just inverses of each other. You know, the 2 flipped over is 1/2. Flipped over, like a reflection. Like these two curves are a reflection of each other. Huh. So here again, yes, our asymptote is the x-axis, which is also y equals 0. So good deal. Very, very good. So I recognize this is very different. This is new. So don't panic. It'll be okay. Let's go and look at number 1 on the next page together and see what we can find out there. So we need to determine if the given series of numbers is going to be a linear relationship or an exponential relationship. Linear, exponential. And the way to look at that is the linear has a constant rate of change. The pattern of behavior is the same throughout. Whereas an exponential, it starts either really growing or really shrinking very quickly. So let's write that down. Linear has a constant rate of change. The ratio of y's to x's is always the same. And that's something we should remember from first semester with straight lines and finding the slope. Exponential it so does not have a constant rate of change. It really multiplies and grows at a crazy rate. To grow or shrink. Not constant. So let's go check those out to see what that would look like on a table. Number 1. So my x values, add 1, add 1, add 1. That's not very exciting. Okay. My y values, add 2, add 4, add 8, add 16, add 32. Is this a constant rate of change? Are we always adding the same amount each time? No way. This is super exponential. Let's look at number 2, just to compare. So number 2, add 1, add 1, add 1, super not exciting. The y's, add 3, add 3, add 3, add 3. Okay, so for this, we had a very constant rate of change of 3 over 1. This is linear all the way. Okay, do you see the difference in how to look at a table to determine if it's linear or if it's exponential? This had the same amount of change for each ratio. This did not. This like blew up. It was about to get real big. So let's look at it from the equation standpoint. When looking at an equation, your big question is, where is the x located? Let's write that down. If it's anywhere other than y equals mx plus b, then it's not linear. If that x is up in an exponent at all, it's exponential. I mean, that's what it is. So number 3, where is the x located? Circle it. Yep, there it is. So that means that this, is it linear or is it exponential? Exponential, that's right. What about number 5? Where is this x located? Circle it. Yep, there it is. Y equals mx plus b. This is linear. Easy, love it. I want you to take just a moment. I want you to do number 4 and number 6. Let me know if you need a little bit of help. Pause the video. Let's look at number 7. So number 7 says evaluate the function if you have this specifically given domain. Let's underline this. And then we want to know, as the domain increases, as it grows, does the range increase or decrease? That's what we need to find out. So let's draw a table. X and Y. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. -2, -1, 0, 1, 2, 3. All right, so there really is a decimal right there. It's hard to see, but I will clarify that. That is a decimal, 0.5. Control Doc. Let's get a graph. Let's type this in. So 0.5 caret x. Hey, that looks very familiar. All right, so let's go get your table so that we can fill in our own. So -2 is 4, and then 2, and 1, and 50 cents, and 25 cents, and finally 12.5 cents. All right, so to answer our question, is this particular range, my blue numbers, are they increasing or decreasing in value? Yeah, they're decreasing, it's shrinking. So I want you to pause the video. I want you to build a table for number 8 with the same domain values that we have here, and then see what the range would be and what its pattern of behavior is.